Alrighty, so this video we're going to do a couple of examples of calorimetry, make sure we understand how to solve these problems correctly, maybe ease a little confusion if there is any. So let's take our first example. Well, first let me go ahead and discuss what it is we need to know to solve these types of problems. Every problem will be solved by you have a system, and that system is composed of multiple pieces. You take the amount of heat energy gained or lost by each piece. Those are called Q. You add them all up and set it equal to 0 because there should be no total change in energy of the system. If you have one piece of your system which loses energy, well, that can only be true if some other piece or multiple pieces gain that energy. And so the total change in the energy must be 0. Whatever's lost is gained, and whatever gained is lost. Now, in order to use this, of course, we need to be able to figure out how much energy is gained or lost for each piece. And to do that, we use Q is equal to Cm delta T, or Cm final minus initial temperature. Okay? Where C is called the specific heat, that tells you what kind of material you're working with, what is the object. M, how much of the object do you have, the mass of the object, and of course delta T is how much the temperature of that object has changed. And so we stick these Q's into that equation, and we're going to solve for whatever unknown it is we have. So let's take an example. This example is you have half a kilogram of coffee, which is sitting at, let's say, 90 degrees Celsius. You would like the coffee to reach 75 degrees Celsius to drink. Okay, so you want to cool it off. How much milk, cold milk, the milk is at 5 degrees Celsius, let's say. How much milk at 5 degrees Celsius should you add to the coffee? And we're going to let the specific heat of coffee be 4,000 and the specific heat of milk be 3,000 for this problem. So there's our problem. We have a system. The system is we're going to combine coffee and milk together. What do we know? We know the coffee. We have half a kilogram of coffee, and that coffee starts at 90 degrees. We're then going to add milk that's starting at 5 degrees to that coffee until we reach a final temperature of 75 degrees. The question is, how much milk should we add? Okay. Well, what are all the pieces of my system? I've got Q for coffee. The coffee's going to lose some heat. And I've got the Q for the milk. The milk is going to gain that heat. And those are the only two pieces in my system, so I set it equal to 0. For each Q, I have Cm delta T. So I have C for coffee, M for coffee, and I have the final temperature minus the initial temperature of the coffee. And then we have the same for the milk. C for milk, mass of the milk, and then final temperature minus the temperature of the milk equals 0. With this, we can plug numbers in. C for coffee, that's 4,000. Mass of the coffee, I had half a kilogram, so 0.5. Remember, the units of mass have to be kilograms. And then I have TF, the final temperature of the system, 75 degrees, minus the initial temperature of the coffee is 90. So there's Cm delta T for coffee. Now I need to do it for milk. What's the specific heat of milk? For this problem, we're calling it 3,000. What's the mass of the milk? I don't know. I don't know how much milk, but that's what I'm looking for. So I have M. That's my unknown. How much milk do I add? And then final temperature of the milk, well, that's the final temperature of the whole thing, which is 75. Minus what was the initial temperature of the milk? I'm told it's at 5 degrees to start with. And then we set that equal to 0. And now we can see our equation. We see we have a whole bunch of numbers and only one unknown sitting there, the little m. And so we could solve. So what do we get? 4,000 times 0.5 times 75 minus 90 is negative 15. And this becomes negative 30,000 plus 3,000 times m times 75 minus 5, which is just 70. So you get 21,000 times m. Okay. And now all we have to do is solve this for m. So we keep m on one side, everything else goes on the other. So 210,000 times m equals 30,000. So m must be 30,000 over 210,000. I get 0.14 kilograms. So how much milk should I add? 0.14 kilograms worth of milk, 140 grams of milk. So we could see this is similar to the question we had in our lecture video. But instead of solving for the final temperature of the system, in this case, I knew what the final temperature was going to be. All I had to do was solve for how much milk is required to create that final temperature. And so I was solving for the mass of the milk. So I hope this makes sense. We'll move on to the next example. Example 2. Let's say we have an ice chest. All that means is there's going to be some place that we can put everything that cuts the system off from the rest of the world. Everything's in a nice closed system. You have an ice chest. You place into it 2 6-packs of beer, whose initial temperature is, let's say, 2 degrees Celsius. You also place a 10 kilogram watermelon whose initial temperature is, let's make him room temperature, let's say 20 degrees Celsius. Finally, you include 3 turkey sandwiches, each of mass 100 grams, whose initial temperature is 10 degrees Celsius. If the mass of each can of beer is, let's say, 250 grams, and the specific heat for beer is, let's say, the same as water, 4186. The specific heat for the watermelon is 4,000, and the specific heat for the turkey is 1,000. Find the final temperature of the system. All right, so I tried to create something a little more complex here. You have a system. The system includes 12 cans of beer, which is at its temperature, a big old heavy watermelon, which is at its temperature, and a couple of turkey sandwiches, which is at their temperature. Put them all into an ice chest and let that thing come to equilibrium. So hopefully the beer will cool everything off. Unfortunately, there's a warm watermelon in there which will heat things up. And I want to know, what will the temperature be? Maybe because I want to figure out, should I include an ice pack in there to try to make sure everything's cold? Or will it be cold enough without an ice pack? Just as a predictor. So how do we go about solving this problem? Well, we're going to do it just like we've done every other calorimetry problem. First thing we include is how many pieces are in our system. Well, there's going to be a Q for the beer. How many will there be? Each beer, I know each beer's mass and each beer's temperature. How many beers are there? 2 6-packs, so I'm going to have 12 of those. 12 times Q for a beer. Then I'm going to have Q for the watermelon. And then I have the turkey sandwiches. There are 3 of them, so I'm going to have 3 Qs for the turkey sandwich. So that's everything in my system. The beers, the watermelon, the turkey, everything's there. Set it equal to 0. Next step, replace all the Q's with Cm delta T. Okay. So I still have 12 out in front. Q for beer becomes C for beer. And what is C for beer? 4186. M for beer, what's the mass of a single beer? 250 grams, so that's 0.25 kilograms. And delta T is final temperature, which is what I'm looking for, minus the initial temperature of the beer, which is 2. degrees. And now we have the watermelon. Q for watermelon, so it's C, which is 4,000. The mass of the watermelon, 10 kilograms, so that's 10. Delta T, final minus initial. Initial temperature was 20. And then the sandwiches, I've got 3. Each one has a specific heat of 1,000. Each one has a mass of 100 grams, so that's 0.1. And final temperature minus initial, the initial temperature was 10 degrees. Okay. So there's my 3 pieces. Set it equal to 0. And now I start calculating what I can. Let me give myself a little room. So what do we have? 12 times 4186 times 0.25 times TF. So that's 12 times 4186 times 0.25 is 12558 TF minus 12 times 4186 times 0.25 times 2. 25116. Okay, so that's the first piece. Next piece, I've got 4,000 times 10 times TF, so that's 40,000 TF, minus 4,000 times 10 times 20, which is 800,000. And then the last piece, I've got 3 times 1,000 times 0.1 times TF. So that's 300 TF. And then 3 times 1,000 times 0.1 times negative 10, which is minus 3,000. And then we set that equal to 0. So now we have our big long equation, whole bunch of numbers, and TF is the only unknown sitting here. So let me collect all the TFs on one side. So what do we get? We have 12558 plus 40,000 plus 300. So we have 52858 TF. And then the other things go on the other side. So I have 25116 plus 800,000 plus 3,000. And on this side I get 828116. And of course, solve for TF. I divide that thing over. And I get TF is 15.67 degrees Celsius. Before I box it, does this make sense? Can it be this answer? Well, what do I know? The hottest thing in my system was at 20 degrees. That was the watermelon. The coldest thing in my system, which was the beer, was at 2. And so I know the answer has to be somewhere between 2 and 20. Here I get an answer of 15, so it makes sense. I could go ahead and box the answer. So what will the final temperature be? 15 degrees. So that tells me if I want everything to be nice and cold for the picnic or whatever it is, I better include some ice packs or a lot of ice or something to try to cool everything down, because that watermelon warmed things up a little too much. 15 degrees Celsius is not a nice chilly beer. You want it a lot colder. But here you can see, even a complicated system with a whole bunch of different pieces, all at different temperatures, all with different specific heats, you're still solving it the way you solved everything else. You just have to be more organized and careful to make sure all the pieces are correct, you're including every piece, you've factored in the fact that there's 3 turkey sandwiches, not just one, or there's 12 cans of beer, not just one, and all this kind of stuff. But as long as you're careful, you multiply everything out, you get a big long equation with a whole bunch of numbers, collect all the variables to one side, everything else on the other side, and you solve. So I hope these examples help, and I hope my explanations help you see how I go about solving these types of problems. I always start the same way. After I read the question, I always ask myself the first main problem, which is, what is every single piece of this system? If you can include every piece, you're going to be fine. Forgetting a piece is where people go wrong. And that comes more into play later when we talk about melting and things. Then things can get a little confusing because you might forget, oh yeah, the ice had to heat up to get to the melting point before it even melted. Things like here, it's fairly obvious. You read the question, you know all the pieces in your system, keep track of them all, make sure you have the, distributing the numbers, multiplying things out correctly, and you should be okay. So keep practicing. Practice the problems that are on Canvas for sure. Go through these again. Try to do these problems by yourself without watching me do them and see if you get the same answer. And as always, if you have any questions, please email me and I'll be happy to try to work your way through them. So until next time.